All right. Okay. Okay, let's wait. Let's wait for confirmation. So I'll go my VC. Let's see if Mr. Oh, there he is. Face of you. I don't know if he's up. Okay, so what it can. Okay, audio's good. So we were here. I don't know if Mr. Evil will join us.
Restart the compute engine behind the Colab notebook and run all the cells to where we are. So let's just see that. Restart and run runtime. If you're getting errors, sometimes this helps. There is no set in stone way to troubleshoot errors. It's guess and check with this. So there we go. We've created 10 zeros, which is torch zeros like our 1 to 10 tensor. So we've got zeros in the same shape as 1 to 10. So if you'd like to create tensors, use torch arrange and get deprecated message. Use torch a range instead for creating a range of tensors with a start and end in a step. And then if you want to create tensors or a tensor like something else, you want to look for the like method. And then you put an input, which is another tensor, and then it'll create a similar tensor with whatever this method here is like in that fashion or in the same shape as your input. So with that being said, give that a try, create a range of tensors, and then try to replicate that range shape that you've made with zeros. I'll see you in the next video.
Okay, so let's do the first one. What was a range? I think the first one was a range. So range is equal to oh, there it is. Torch a range. I can't see. Let's run it. It's probably gonna fail because we need to run everything with Control F9, right? So connected. Okay, Control F9. So this is a range of 0 to 10. I think it's going to be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Yes. So that was range. What was the next one he said? Zeros like. Towards zeros like input range. Okay. Good. All right.
Welcome back. Let's now get into a very important topic of tensor data types. So we've briefly hinted on this before, and I said that let's create a tensor to begin with, float32 tensor, and we're going to go float32 tensor equals torch.tensor, and let's just put in the numbers 3, 6, 9. If you've ever played Need for Speed Underground, you'll know where 369 comes from. And then we're going to go dtype equals, let's just put none and see what happens, hey? Float32 tensor. Oh, what is the data type? Float32 tensor.dtype. Float32, even though we put none. This is because the default data type in PyTorch, even if it's specified as none, is going to come out as float32. What if we wanted to change that to something else? Well, let's type in here, float16. And now we've got float32 tensor. This variable name is a lie now because it's float16 tensor. So we'll leave that as none. Let's go there. There's another parameter when creating tensors that's very important, which is device. So we'll see what that is later on. And then there's a final one, which is also very important, which is requires grad equals false. Now, this could be true, of course. We're going to set this as false. So these are 3 of the most important parameters when you're creating tensors. Now, again, you won't necessarily always have to enter these when you're creating tensors because PyTorch does a lot of tensor creation behind the scenes for you. So let's just write out what these are. Data type is what? Data type is the tensor, e.g. float32 or float16. Now, if you'd like to look at what data types are available for PyTorch tensors, we can go torch.tensor. And right up the top, unless the documentation changes, we have data types. It's so important that data types is the first thing that comes up when you're creating a tensor. So we have 32-bit floating point, 64-bit. If you'd like to look at what data types are available for PyTorch tensors, we can go torch.tensor. And right up the top, unless the documentation changes, we have data types. It's so important that data types...
Okay. Today we'll use this thing, copy. Somebody wants to join us from the stream. Yeah, I don't know if he's coming. Wait, that's me.
Is the first thing that comes up when you're creating a tensor. So we have 32-bit floating point, 64-bit floating point, 16, 32-bit complex. Now, the most common ones that you will likely interact with are 32-bit floating point and 16-bit floating point. Now, what does this mean? What do these numbers actually mean? Well, they have to do with precision in computing. So let's look up that. Precision in computing. Precision, computer science. So in computer science, the precision of a numerical quantity, we're dealing with numbers, right, is a measure of the detail in which the quantity is expressed. This is usually measured in bits, but sometimes in decimal digits. It is related to precision in mathematics, which describes the number of digits that are used to express a value. So for us, precision is the numerical quantity, is a measure of the detail, how much detail in which the quantity is expressed. So I'm not going to dive into the background of computer science and how computers represent numbers. The important takeaway for you from this will be that single precision floating point is usually called float 32, which means, a number contains 32 bits in computer memory. So if you imagine, if you have a tensor that is using 32-bit floating point, the computer memory stores the number as 32 bits. Or if it has 16-bit floating point, it stores it as 16 bits, or 16 numbers representing, or 16, I'm not sure if a bit equates to a single number in computer memory. But what this means is that a 32-bit tensor is single precision. This is half precision. Now, this means that the default is 32, float 32, torch.float 32, as we've seen in code, which means it's going to take up a certain amount of space in computer memory. And you might be thinking, why would I do anything other than the default? Well, if you'd like to sacrifice some detail in how your number is represented, so instead of 32 bits, it's represented by 16 bits, you can calculate faster on numbers that take up less memory. So that is the main differentiator between 32-bit and 16-bit. But if you need more precision, you might go up some detail in how your number is represented. So instead of 32 bits, it's represented by 16 bits. You can calculate faster on numbers that take up less memory. So that is the main differentiator between 32-bit and 16-bit. But if you need more precision, you might go up to 64-bit. So just keep that in mind as you go forward. Single precision is 32, half precision is 16. What do these numbers represent? They represent how much detail a single number is stored in memory. That was a lot to take in, but we're talking about tensor data types. I'm spending a lot of time here because I'm going to put a note here. Note, tensor data types is one of the three big issues with PyTorch and deep learning. Or not issues, they're going to be errors that you run into all the time on numbers that take up less memory. So that is the main differentiator between 32-bit and 16-bit. But if you need more precision, you might go up to 64-bit. So just keep that in mind as you go forward. Single precision is 32, half precision is 16. What do these numbers represent? They represent how much detail a single number is stored in memory. So that was a lot to take in, but we're talking about tensor data types. I'm spending a lot of time here because I'm going to put a note here. Note, tensor data types is one of the three big issues with PyTorch and deep learning. Or not issues, they're going to be errors that you run into in deep learning. Three big errors you'll run into with PyTorch and deep learning. So one is tensors not right data type. Two, tensors not right shape. We've seen a few shapes before. And three, tensors not on the right device. And so in this case, if we had a tensor that was float 16 and we were trying to do computations with a tensor that was float 32, we might run into some errors. And so that's the tensors not being in the right data type. So it's important to know about the d-type parameter here. And then tensors not being the right shape, well, that's once we go into matrix multiplication, we'll see that if one tensor is a certain shape and another tensor is another shape, and those shapes don't line up, we're going to run into shape errors. And this is a perfect segue to the device. Device equals none. By default, this is going to be CPU. This is why we are using Google Colab, because it enables us to have access to, we don't want to restart, enables us to have access to a GPU. As I've said before.
Wait, I didn't get that. What's the shape? I didn't, what?
And then the tensors not being the right shape, well, that's once we go into matrix multiplication, we'll see that if one tensor is a certain shape and another tensor is another shape.
Oh, but it's nothing to do with these parameters, okay.
And those shapes don't line up, we're going to run into shape errors. And this is a perfect segue to the device. Device equals none. By default, this is going to be CPU. This is why we are using Google Colab, because it enables us to have access to, we don't want to restart, enables us to have access
Wait, what?
to a GPU. As I've said before, a GPU enables us.
Tensor data types is one of three big errors you'll, oh, this is his book, I guess.
So we could change this to CUDA. That would be, we'll see how to write device agnostic code later on. But this device, if you try to do operations between two tensors that are not on the same device, so for example, you have one tensor that lives on a GPU for fast computing, and you have another tensor that lives on a CPU, and you try to do something with them, well, PyTorch is going to throw you an error. And then finally, this last requires grad, is if you want PyTorch to track the gradients, we haven't covered what that is, of a tensor when it goes through certain numerical calculations. This is a bit of a bombardment, but I thought I'd throw these in as important parameters to be aware of, since we're discussing data type. And really, it would be reminiscent of me to discuss data type without discussing not the right shape or not the right device. So with that being said, let's write down here what device is your tensor on, and whether or not to track gradients with this tensor's operations. So we have a float 32 tensor. Now, how might we change the tensor data type of this? Let's create float 16 tensor. And we saw that we could explicitly write in float 16 tensor, or we can just type in here float 16 tensor equals float 32 tensor dot type, and we're going to type in torch.float 16. Why float 16? Because, well, that's how we define float 16, or we could use half. So the same thing. These things are the same. Let's just do half. Or float 16 is more explicit for me. And then let's check out float 16 tensor. Beautiful. We've converted our float 32 tensor into float 16. So that is one of the ways that you'll be able to tackle the tensors not in the right data type issue that you run into. And just a little note on the precision of computing. If you'd like to read more on that, I'm going to link this in here. And this is all about how computers store numbers. So precision in computing. There we go. I'll just get rid of that. Wonderful. So give that a try. Create some tensors, research, or go to the documentation on torch.tensor and see if you can find out a little bit more about d-type device and requires grad. And create some tensors of different data types. Play around with whatever the ones you want here and see if you can run into some errors. Maybe try to multiply two tensors together. So if you go float 16 tensor times float 32 tensor, give that a try and see what happens. I'll see you in the next video.
Okay, that's an interesting test to run. Sorry. Okay, so let's do float 16 tensor is equal to torch tensor I don't know what he did. Maybe 1, 2, 3. And then D-type, yeah. Now let's create another one. That's 64 and tell it $64. This is 64, and now we don't need to say that. We can just oh, look, it understands. No, multi. I said multi. It there it is. Should get an error. We didn't get an error. So what if we create another guy, like he said? Can't see the cursor. This is going to be 32. 32. 32. And then let's multiply, like he said, mul2 is equal to float 16 tensor. No, it doesn't autocomplete. Float 16 tensor multiplied by you're connected but not utilizing float 32. I can't see. It doesn't just print. So print this. There's no error. So he promised us an error. So I don't know what's going on.
Welcome back. In the last video, we covered a little bit about tensor data types, as well as some of the most common parameters you'll see passed to the torch.tensor method. And so I used to do the challenge at the end of the last video to create some of your own tensors of different data types, and then to see what happens when you multiply a float 16 tensor by a float 32 tensor. Oh, it works. But you're like, Daniel, you said that you're going to have tensors not the right data type. Well, this is another kind of gotcha or caveat of PyTorch and deep learning in general, is that sometimes you'll find that even if you think something may error because these two tensors are different data types, it actually results in no error. But then sometimes you'll have other operations that you do, especially training large neural networks, where you'll get data type issues. The important thing is to just be aware of the fact that some operations will run an error when your tensors are not in the right data type. So let's try another type. Maybe we try a 32-bit integer. So torch.int32, and we try to multiply that by a float. Wonder what will happen then. So let's go int32 tensor.
This is a waste of time.
Equals torch.tensor, and we'll just make it 3. Notice that there's no floats there, or no dot points to make it a float. 369, and d type can be torch int32. And then int32 tensor, what does this look like? Typo, of course, one of many. Int32 tensor. So now let's go float32 tensor and see what happens. Can we get PyTorch to throw an error? Int32 tensor.
I gamble there is not going to be an error. It's all going to be float.
Huh, it worked as well. Or maybe we go int64.
This is why it's no, it's going to work. It's everything. No, there's not going to be an. Oh, maybe int64 might give you an issue.
It still works. Now, see, this is again one of the confusing parts of doing tensor operations. What if we do a long tensor?
Oh long. My god! Why is he wasting so much
there's no attribute called long. That's not a data type issue. I think it's long tensor. Long tensor. Does this work? D type must be torch D type. Torch long tensor. I could have sworn that this was torch.tensor. Oh, there we go. Torch.long tensor. That's another word for 64-bit. So what is this saying? CPU tensor. Okay, let's see. This is some troubleshooting on the fly here.
He doesn't have autocomplete. Everything works for him.
We multiply it. This is a float 32 times long. It works. Okay, so it's actually a bit more robust than what I thought it was. But just keep this in mind when we're training models. We're probably going to run into some errors at some point of our tensors not being the right data type. And if PyTorch throws us an error saying your tensors are in the wrong data type, well, at least we know now how to change that data type or how to set the data type if we need to. And so with that being said, let's just formalize what we've been doing a fair bit already, and that's getting information from tensors. So the three big things that we'll want to get from our tensors, in line with the three big errors that we're going to face in neural networks and deep learning, is, let's copy these down. Just going to get this, copy this down below. So if we want to get some information from tensors, how do we check the shape? How do we check the data type? How do we check the device? So let's write that down. So to get information from this, to get D type, or let's write data type from a tensor, can use tensor.dtype. And let's go here. To get shape from a tensor, can use tensor.shape. And to get device from a tensor, which device is it on, CPU or GPU, can use tensor.device. Let's see these three in action. So if we run into one of the three big problems in deep learning and neural networks in general, especially with PyTorch, tensor's not the right data type, tensor's not the right shape, or tensor's not on the right device, let's create a tensor and try these three out. We've got some tensor equals torch.rand, and we'll create a 3, 4. Let's have a look at what it looks like. There we go. Random numbers of shape 3 and 4. Now let's find out some details about it. Find out details about some tensor. So we'll print some tensor, and oops, didn't want that. Print, and let's format it, or make an F string of shape of tensor. Or let's do data type first. We'll follow that order. Data type of tensor, and we're going to go, how do we do this? Some tensor dot what? Dot D type, beautiful. And then we're going to print tensor's not in the right shape. So let's go shape of tensor equals some tensor dot shape. Oh, I went a bit too fast, but we can also use size. Let's just confirm that actually. We'll code that out together. From my experience, some tensor dot size and some tensor dot shape result in the same thing. Is that true? Oh, function. Oh, that's what it is. Some tensor dot size is a function, not an attribute. There we go. Which one should you use? For me, I'm probably more used to using shape. You may come across dot size as well, but just realize that they do
Interesting. Size and shape are the same. Wow.
quite the same thing, except one's a function and one's an attribute. An attribute is written dot shape without the curly brackets. A function or a method is
These are not curly. These are parentheses.
with the brackets at the end. So that's the difference between
No, these are not brackets. Jesus.
these attributes here. D type, size, we're going to change this to shape. Tensor attributes. This is what we're getting. I should probably write that down. This is tensor attributes. That's the formal name for these things. And then finally, what else do we want? Tensors, what device are we looking for? Let's get rid of this, get rid of this. And then print F device. Tensor is on. By default, our tensor is on the CPU. So some tensor dot device. There we go. So now we've got our tensor here, some tensor. The data type is a torch float 32 because we didn't change it to anything else, and torch float 32 is the default. The shape is 3, 4, which makes a lot of sense because we passed in 3, 4 here. And the device tensor is on is the CPU, which is of course the default, unless we explicitly say to put it on another device. All the tensors that we create will default to being on the CPU rather than the GPU. And we'll see later on how to put tensors and other things in Torch onto a GPU. But with that being said, give it a shot, create your own tensor, get some information from that tensor, and see if you can change these around. So see if you could create a random tensor, but instead of float 32, it's a float 16. And then probably another extracurricular, we haven't covered this yet, but see how to change the device a PyTorch tensor is on. Give that a crack.
Yeah, you showed how to do it. Okay, so we want dot D type, dot shape, dot device. Okay. So rand equals torch random. Okay. And then, come on. What's the next step? Then we want to do print D type shape device. How does it know? Didn't I run it? So it's float 32, size is 3 by 4, and it's on the CPU. Well, there you go.
And I'll see you in the next video.
Manipulating tensors, tensor operations.
Welcome back. So in the last video, we had a look at a few tensor attributes, namely the data type of a tensor, the shape of a tensor, and the device that a tensor lives on. And I alluded to the fact that these will help resolve 3 of the most common issues in building neural networks, deep learning models, specifically with PyTorch. So tensors not being the right data type, tensors not being the right shape, and tensors not being on the right device. So now let's get into manipulating tensors. And what I mean by that, so let's just write here the title, manipulating tensors, and this is going to be tensor operations. So when we're building neural networks are comprised of lots of mathematical functions that PyTorch code is going to run behind the scenes for us. So let's go here. Tensor operations include addition, subtraction, and these are the regular addition, subtraction, multiplication. There's 2 types of multiplication that you'll typically see referenced in deep learning and neural networks: division and matrix multiplication. And these, the ones here, so addition, subtraction, multiplication, division, are your typical operations that you're probably familiar with. Matrix multiplication. The only different one here is matrix multiplication. We're going to have a look at that in a minute. But to find patterns in numbers of a data set, a neural network will combine these functions in some way, shape, or form. So it takes a tensor full of random numbers, performs some kind of combination of addition, subtraction, multiplication, division, matrix multiplication. It doesn't have to be all of these. It could be any combination of these to manipulate these
What's the difference between element-wise and matrix multiplication? Oh, okay, yeah.
numbers in some way to represent a data set. So that's how a neural network learns, is it will just comprise these functions, look at some data to adjust the numbers of a random tensor, and then go from there. But with that being said, let's look at a few of these. So we'll begin with addition. First thing we need to do is create a tensor. And to add something to a tensor, we'll just go torch tensor. Let's go 1, 2, 3. add something to a tensor is tensor plus. We can use plus as the addition operator, just like in Python. Tensor plus 10 is going to be tensor 11, 12, 13. Tensor plus 100 is going to be, as you'd expect, plus 100. Let's leave that as plus 10 and add 10 to it. And so you might be able to guess how we would multiply it by 10. So let's go multiply tensor by 10. We can go tensor star, which on my keyboard is shift 8, 10. We get 10, 10, 10. And because we didn't reassign it, our tensor is still 1, 2, 3. So if we reassign it here, tensor equals tensor by 10, and then check out tensor, we've now got 10, 20, 30. And the same thing here. We'll have 10, 20, 30. But then if we go back from the top, if we delete.
1 second, I have a phone call. Okay, let me see. I need to take care of something. One second. One second. Okay. This we can share, even though nobody's in the room. Bloom, bloom. So this is multiplication.
Delete this, reassignment. Oh, what do we get there? Tensor by 10. Oh, what's happened here? Oh, because we've got, yeah, okay, I see. Tensor by 10, tensor. Still 1, 2, 3. What should we try now? How about subtract? Subtract 10 equals tensor minus 10. And you can also use, well, there we go, 1 minus 10, 8 minus 10, 3 minus 10. You can also use, like Torch has inbuilt functions, or PyTorch. So try out PyTorch inbuilt functions. So torch.mul is short for multiply. We can pass in our tensor here and we can add in 10. That's going to multiply each element of tensor by 10. So just taking the original tensor that we created, which is 1, 2, 3, and performing the same thing as this. I would recommend, where you can, use the operators from Python. If for some reason you see torch.mul.
1 second. Okay.
Maybe there's a reason for that, but generally these are more understandable if you just use the operators. If you need to do a straight up multiplication, straight up addition, or straight up subtraction, because Torch also has torch.add. Torch.add, is it torch.add? It might be torch.add, I'm not sure. Oh, there we go. Yeah, torch.add. So as I alluded to before, there's two different types of multiplication that you'll hear about, element-wise and matrix multiplication. We're going to cover matrix multiplication in the next video. As a challenge, though, I would like you to search what is matrix multiplication. And I think the first website that comes up, Matrix Multiplication Wikipedia. Yeah, Math is Fun has a great guide. So before we get into matrix multiplication, jump into Math is Fun to have a look at matrix multiplying and have a think about how we might be able to replicate that in PyTorch. Even if you're not sure, just have a think about it. I'll see you in the next video. How we might be able to replicate that in PyTorch. Even if you're not sure, just have a think about it. I'll see you in the next video.
So he did not teach matrix multiplication, just I guess addition, subtraction, multiply. He didn't even do division. Okay. Get out. So let's define. Did he define? Oh, tensor 1, 2, 3. Okay. So tensor equals torch tensor 1, 2, 3. How does he know? Weird. Okay, plus 10. And minus 10. And times 10. Let me check. One second. So this is times 10. So we can also do, he didn't do, but we can do divided by 10. Oopsie doopsie. Good. And that's it. That's he also taught the mul, the add, the functions, but I don't care. Let me check this. Okay.
Next video. Welcome back. In the last video, we discussed some basic tensor operations, such as addition, subtraction, multiplication, element-wise.
Okay, one second. Okay, just gotta do some stuff. So forward this to this guy. And now, this guy. This guy. That was two, now the third. Wow, come on, so slow. Forward. This guy. So this was the third. Now the fourth. Now the fifth. 1, 2, 3, 4, 5. Mm-hmm. Okay. 1, 2, 3, 4, 5, 6. Jesus Christ, how slow can it be? Oh my God. Okay. One, two, three, 4, 5, 6, 7. Let me write it down. This is 7. Okay, 7. 1, 2, 3, 4, 5, 6, 7, 8. Oh my God. Kill me already. Kill me, please. Kill me. Okay. Last one. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. Wait, did I send it? I don't know. Yeah, I think the last one I sent twice. So let's check the numbers. So 1, 2, 3, 4, 5, 6, 7, 8, 9 exactly. Wait. So she asked me to send it. She gave me the contact, right? I think she gave me the contact. Let me check. This guy. No. This guy. All right, so now we need Okay, so I should have it. Where is my stuff? I have to go soon. No. There it is. Okay. Okay. Oh my god. This guy? So this, well, let's just select this and this and send it to. So let's create a new thing. This is so terrible. Okay, so I want to send this to this guy. Okay. Okay. So everything is almost ready. Just need a few more documents. What is that? Okay. Wait, do I actually? Maybe I already have this document. Let me check. Check it. So it should be here. No, I don't have it. Don't have it. Okay, I don't have it, so let's wait for it. Everything is so fast today. Oh my god, everything is right away. What's going on? What is going on here? Why is she not sending it? Jesus Christ. What is going on? Oh my god. Okay. So I think we're done with this. We're done with almost everything. Wait, what did she say? Let me see. Did she say something? No. I don't know. Okay, whatever. Okay, so that's division. All right, what's the next thing he's doing?
Division and matrix multiplication, but we didn't actually go through what matrix multiplication is. So now let's start on that, more particularly discussing the difference between element-wise and matrix multiplication. So we'll come down here. Let's write another heading, matrix multiplication. So there's two ways, or two main ways. Yeah, let's write that. Two main ways of performing multiplication in neural networks and deep learning. So one is the simple version, which is what we've seen, which is element-wise multiplication. And number two is matrix multiplication. So matrix multiplication is actually possibly the most common tensor operation you will find inside neural networks. And in the last video, I issued the extra curriculum of having a look at the mathsfun.com page for how to multiply matrices. So the first example they go through is element-wise multiplication, which just means multiplying each element by a specific number. In this case, we have 2 times 4 equals 8, 2 times 0 equals 0, 2 times 1 equals 2, 2 times negative 9 equals negative 18. Then if we move on to matrix multiplication.
1 second. Jesus Christ. Okay, whatever. Good enough. Okay. Yeah. It's not good that it's this format. Let me try. Come on, what's wrong with the... Okay, so this I'm gonna cut off here. This I'm gonna cut off here. So this we're gonna add to this. Okay. All right. Let's see. second. Okay.
Which is multiplying a
I
matrix
think I should skip this. I don't need this.
by another matrix. We need to do the dot product. So that's something that you'll also hear matrix multiplication referred to as the dot product. So these two are used interchangeably, matrix multiplication or dot product. And if we just look up the symbol for dot product, you'll find that it's just a dot. There we go, a heavy dot. Images. There we go, A dot B. So this is vector A dot product B. A few different options there, but let's look at what it looks like in PyTorch code. But first, there's a little bit of a difference here.
That's vector. Vector dot is it the same? Is there a matrix dot? Never heard of anyone say matrix dot product.
So how did we get from multiplying this matrix here of 1, 2, 3, 4, 5, 6 times 7, 8, 9, 10, 11, 12? How did we get 58 there? Well, we start by going, this is the difference between element-wise and dot product, by the way. 1 times 7, we record that down there, so that's 7. And then 2 times 9, so this is first row, first column. 2 times 9 is 18. And then 3 times 11 is 33. And if we add those up, 7 plus 18 plus 33, we get 58. And then if we were to do that for each other element that's throughout these two matrices, we end up with something like this. So that's what I'd encourage you to go through step by step and reproduce this. A good challenge would be to reproduce this by hand with PyTorch code. But now,
1 second. Okay. So let me see. This one. No. Let me check this one. Okay. So I'm gonna send this to this. Okay, now I'm going to look at this. Where is okay. Okay, now, so let me start sending everything. So the first thing is this. What's his name? Oh my God. Okay. Okay. And now, one, two, three, 4, 5, 6, 7, 8, 9. Okay, so now we need to make a note. No. No. Mm-hmm. Okay, next. Next is no. Again. No. And the last one. Okay. I think that's everything. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah. Okay, that's everything. All right. Soon I'm gonna have to go.
Let's go back and write some PyTorch code to do both of these. So let's try a link here as well. More information on multiplying matrices. So I'm going to turn this into Markdown. Let's first see element-wise. Element-wise multiplication. We're going to start with just a rudimentary example. So if we have our tensor, what is it at the moment? It's 1, 2, 3. And then if we multiply that by itself, we get 1, 4, 9. But let's print something out so it looks a bit prettier than that. So print, I'm going to turn this into a string. And then we do that. So if we print tensor times tensor, element-wise multiplication is going to give us print equals, and then let's do in here tensor times tensor. We go like that. So we get 1 times 1 equals 1. 2 times 2 equals 4. 3 times 3 equals 9. Now, for matrix multiplication, PyTorch stores matrix multiplication similar to torch.mul in the torch.matmul space, which stands for matrix multiplication. So let's just test it out. Let's just do the exact same thing that we did here. Instead of element-wise, we'll do matrix multiplication on our 1, 2, 3 tensor. What happens here? Oh my goodness, 14. Now, why did we get 14 instead of 1, 4, 9? Can you guess how we got to 14 or think about how we got to 14 from these numbers?
So 1 times 1 plus 2 times 2 plus 3 times 3. So it's 9 plus 4 is 13, 14. Yeah.
Recall back, we saw that we're only multiplying two smaller tensors, by the way, 1, 2, 3. This example is with a larger one. The same principle applies across different sizes of tensors or matrices. And when I say matrix multiplication, you can also do matrix multiplication between tensors. And in our case, we're using vectors, just to add to the confusion. But what is the difference here between element-wise and dot product? Well, we've got one main addition, and that is addition. So if we were to code this out by hand, matrix multiplication by hand, recall that the elements of our tensor are 1, 2, 3. So if we wanted to matrix multiply that by itself, we'd have 1 times 1, which is the equivalent of doing 1 times 7 in this visual example. And then we'd have plus, it's going to be 2 times 2, 2 times 2. What does that give us? Plus
4.
3 times 3. What does it give us? 3 times 3.
9.
That gives us 14. So that's how we got to that number there. Now, we could do this with a for loop. So let's have a gaze at, when I say gaze, it means have a look. That's an Australian colloquialism for having a look. But I want to show you the time difference in, it might not actually be that big a difference if we do it by hand versus using something like matmul. And that's another thing to note is that if PyTorch has a method already implemented, chances are it's a fast calculating version of that method. So I know for basic operators, I said it's usually best to just use a straight up basic operator. But for something like matrix multiplication or other advanced operators instead of the basic operators, you probably want to use the torch version rather than writing a for loop, which is what we're about to do. So let's go value equals 0. This is matrix multiplication by hand. So for I in range len tensor, so for each element in the length of our tensor, which is 1, 2, 3, we want to update our value to be plus equal, which is doing this plus reassignment here, the ith element in each tensor times the ith element, so times itself. And then how long is this going to take? And let's now return the value. We should get 14. Right? 14, there we go. So 1.9 milliseconds on whatever CPU that Google Colab is using behind the scenes. But now if we time it and use the torch method, torch.matmul, equals tensor.tensor. And again, we're using a very small tensor, so okay, there we go. It actually showed how much quicker it is, even with such a small tensor. So this is 1.9 milliseconds. This is 252 microseconds. So this is 10 times slower using a for loop than PyTorch's vectorized version. I'll let you look into that if you want to find out what vectorization means. It's just a type of programming that rather than writing for loops, because as you could imagine, if this tensor was, let's say, had 1 million elements instead of just 3, if you had to loop through each of those elements one by one, then that's going to be quite cumbersome. So a lot of PyTorch's functions behind the scenes implement optimized functions to perform mathematical operations such as matrix multiplication, like the one we did by hand, in a far faster manner, as we can see here. And that's only with a tensor of 3 elements. So you can imagine the speed ups on something like a tensor with 1 million elements. But with that being said, that is the crux of matrix multiplication. For a little bit more, I encourage you to read through this documentation here by mathistein.com. Otherwise, let's look at a couple of rules that we have to satisfy for larger versions of matrix multiplication. Because right now, we've done it with a simple tensor, only 1, 2, 3. Let's step things up a notch in the next video.
Okay, let me
Matrix multiplication. Because right now, we've done it with a simple.
I wanted to see. Yeah, this loop is interesting to me. Very interesting to me. So let's do matrix multiplication. Wait, what? Okay, so let's do matrix multiplication. So it's actually a vector. So let's say V1 is torch. Yeah, V2, that's good. I need to do Control F9 to restart everything. What's wrong? So, yeah. Still? What's wrong? Name torch is not defined. Okay, try it again. Shift, yeah. So it's 41018. Okay, so it's field-wise multiplication. And now let's do dot equals, how do you do it? I think you do V1 matrix multiply V2. Yeah. Why is it not running? Oh, you need to say dot. Tensor 32. So is this correct? It's 1 times 4 plus 10 plus 18, 28 plus 4, 32, correct. Now let's try to write the loop. I don't remember how to do the loop. It's like let me see. So he says for I in range len tensor, Jesus Christ, colon. All right, let's try it. Well, maybe it will complete me. For I in, what is it? For I in range, len I in range then of a tensor, which is v1, value plus equals tensor 1, tensor 2. Okay, so we need to first val equals 0, and then we're going to say val, yeah, exactly, and then we're going to print, okay, which is this, like this. For colon is missing, okay. Tensor object is not callable. Len, I don't know if there's len. Maybe there's torch len. Wait, he just said len. Range len tensor. Range len v1. What's wrong? Tensor object is not callable. Wait, range? For I in range. Oops. For I in range. For I in range len tensor. I don't know what's going on. Let's try. Oh, we can't copy this. For I in range len tensor colon. For I in range len. I don't know what's going on. It says tensor object is not callable. Who's trying to? Tensor object is not callable. Tensor object is not callable. Weird. Let's try this again. No. So it worked for him. For I in range of len of tensor and tensor, he defined tensor as vector. Like we defined v1. v1 is a torch tensor. I don't know. Don't know. So look, this is just 3 in case we need to. Still nothing? I need. Did we create the tensor correctly? Torch tensor. I don't see an issue with it. Type error. Explain. Oh, let's try this. Explain error. The error type error tensor object is not callable is raised in line 2 within the loop. This error typically. 1 second. Okay, 1 second. I have a message. Okay, so that's done. That's done. Next, so what is he saying? For iron torch a range. Well, there you go. I was suspecting because, yeah. Okay, let's try this. Okay, so that was the reason. And we want to see the time. So he said percent time before. So before you do this, you say percent time not found. Okay, why is that? Isn't this? Didn't he mention? Maybe I missed it. Time not found. Well, that's weird. And there's no way to get help for this?
Operators instead of the basic operators, you probably want to use the torch version rather than writing a for loop, which is what we're about to do. So let's go value equals 0. This is matrix multiplication by hand. So for
So he didn't even say
use the torch version rather than
anything
writing a
about
for loop, which is what we're about to do. Matrix
Wait.
version of something like matmul. Having a look. But now we could do this with a for loop. So let's have a gaze at, when I say gaze, it means have a look. That's an Australian colloquialism for having a look. But I want to show you the time difference in, it might not actually be that big a difference if we do it by hand versus using something like matmul. And that's another thing to note is that if PyTorch has a method already.
Let's see. So let's give it a prompt with percent time. This is a Jupyter Notebook magic command that is placed in the beginning of a cell. It measures, but this is not a. Is this Jupyter? I think Google Colab is a Jupyter project. The rest, okay. Okay, but let's incorporate time to measure execution time. Percent time. Use code with caution. This is a Jupyter. The rest of the cell contains a PyTorch. Okay, let me just take this. Okay. Bring it here. Ask it what's going on. So the error not found indicates that the time magic command is not available in your current Jupyter Notebook environment. This can happen if the necessary extensions are not loaded, if there are conflicts with other extensions. Here's how you can address this issue. Pip install IPython. Jesus. Oh my God. What a nightmare. This is terrible. What is all this? We need all this to make it available? Oh. Still not working, so it's useless. So it doesn't work Let's see. Did anybody ask?
Text from the initial encoding. The vector associated with the word fluffy.
Did anybody ask him? Discussion. Can we search? No. Can we search in this? Just in general, can you search for that? How do you use this thing? Time. Is it possible to search? Maybe just the word time? Is it searching? Is it giving me any results? What's going on? It doesn't look like it's changing. Let's remove everything. %% time. I don't think it's. I don't know. How do you ask a question? Oh, maybe I'm not logged in? Oh, I'm not logged in. Let me stop. Let me stop the transmission and log in. So in order to log in, I would go here and click on sign in. I guess I have to create a new account. What? Are you kidding me? I have to create a password? This is nonsense. Jesus. Well, what if I try to already sign in with a passkey? No. Now I need to create an account. Alright, it's going to be same as my email. Where's my email? Oh my God. Okay, where is my Gmail? Okay, that's the email. So now I'm gonna give you my email password. Oh, already associated. Sign in with this email password. So I need to look up my password. Let me just make sure everything is clear. This is okay. This one. 1, 2, 3, 4, 5. This one. Okay. Just making sure all is clear. So, yeah, we need to look it up. I don't know. I don't see it. What's the name? GitHub. I don't see it. Oh my God, I have to look it up. Jesus. Soon I'm gonna have to go. So this. Oh my God, why is it so slow? Okay, so where I don't see anything. Jesus, nothing. Oh my God, I don't have anything. Where is it? Where is it? No, don't have it. This is so weird. Okay, that's weird. Let me look it up. This is called GitHub. Okay. No, I don't see anything. How could this be? Try this. Nothing. So I don't understand. All right, let's try. Try this. Use the arrows to rotate the object to face in the direction of the hand. I think an AI today can already solve all these puzzles better than humans. Send, reset, return. Okay. There it is. There it is. So we need to come up with something. Wait a minute. Switch. I see the problem. Okay, I see. Okay. So git got it. All right. So what's it gonna be? What's it gonna be? Oh, come on. Come on. Come on. Come on. All right, let's see. I guess this would be good. Not so much. Try this. This one. Okay, got it. Okay, try this. Wait, what? What just happened? Hmm. Jesus Christ, what a nightmare. So this is it, and no, this is it, and the other one is this. Mm-hmm. Mm-hmm. Okay. So we're done with this, with this, with this, with this. Okay. Don't care where this guy. Okay. Let's just keep closing. No, no, no. Mm-hmm. Mm-hmm. Okay. Mm-hmm. Everything is fine. We can close this and this. Okay. So can't believe it. You talk to people. It's all pictures. You're not writing in an academic way. You're not following the standard academic format. If you understand anything, then this should be enough. You shouldn't need any pictures. This should be enough. That's it. You shouldn't need any more. This explains everything. This, if Einstein read this, he would have said, perfect. Perfect. That's the foundation of special relativity. You talk to idiots. Wait, you're not saying it. You talk to idiots and they tell you, You have delusions of grandeur. You have delusions. Are you going to talk about the actual paper, the content? No, you have delusions of grandeur. You have delusions of grandeur. That's it. Yeah, that's all they got. You have delusions of grandeur. How could you be smarter than Einstein? Einstein was Jesus. You can't be smarter than Jesus. Oh, that's it. That's it. That's it. Well, hopefully soon I'll be free and I'll be able to do other things. Anyway, let's continue. Wait, did I? Yeah, I'm sharing. Everything is fine. No, we need to. This is ready papers. That's fine. Everything is fine. Oh my God. It's it's so dangerous. It's dangerous to talk to some people. They're just dangerous. They're just gonna get you in trouble. So just have to watch out. The internet is the real jungle. I mean, there's many jungles. Just have to be very careful. Okay, let me see. Are we okay? So I'm gonna have to leave when I should probably start getting ready. Oh my God. Oh my God, this is so terrible. Okay, let's see. Let's shut off everything and let's prepare to drive. Let's see that I have. Hold on. Okay, so if I leave now, it's too early. Okay. But soon I'm gonna have to go. Anyway, so he says, so where, okay, so we wanted to do the time. I don't know what to do about the time, so I wanted to ask him a question. How can oh, new discussion. That's what I was missing. So general ideas, polls, Q&A, I guess general. So this has to do, well, I have to look it up in his book first. Where is his book? I think it should be maybe here. Okay, welcome tutorial course outline about that. Where's the book? Oh, 1 second. So go to actually go to go to slides. Custom computer vision. No. Workflow. I guess 00. All this is 00. No. 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 Something is wrong. Where? Workflow provides other approaching deep learning problems and building neural deep learning. Where are we? What chapter are we in? How can I know what is the chapter? Come on. All right. So this is all 00 PyTorch fundamentals video. Okay. So I don't know. Paper replication, experiment tracking. What is he talking about? Let's see this. Can you be slower? What's going on? Why is it so slow? What's going on? What did we ask for? Where's the book? About this course status log. Online book version, this guy. Oh, okay. So this should be 0, 0. So let's just look for time. No. There you go. So yeah, there's no mention of it. He just says it. It doesn't work for me. Nothing. Okay, then we have to ask a question. So back to here. So we're asking a question about time. Error message, and the error message is this guy. So just usage. So just give me like this. Copy code. Where's the code? Where? I didn't put it? Didn't I put it somewhere? How did it? Oh. Are you insane? So all this time I was trying to do something that actually does work? So the answer is you have to put it at the top. Oh. Well. Okay, I mean, we didn't completely waste our time, I guess. Let's see. The battery. What's the situation? Okay, this we can do. And this is fine. Terrible. Just terrible. Okay. Okay, so that was interesting. So now this multiplication is not interesting. This multiplication is interesting. And this multiplication is interesting. And that's the difference is this is 90 microseconds and this is 264 microseconds. Okay. That's all I wanted. And this we can get rid of. Unless it actually did solve the problem, probably not. Okay. What is it? Okay. Yeah, I gotta go. All right, everyone. Wait, did I? No, I didn't do that. Okay, let's leave this. By the way, they gave me this gulag, these idiots, because they said, because of the discussion, somebody reported me, some idiot reported me. Where is it? Where? This one. Everything I said, they put me in this gulag. They gave me whatever, a strike, a gulag. They said that I mentioned children inappropriately. We had a debate, of course, about pedophilia, and I took it down. I took the video down because it was just like an hour of yelling that they're just gonna malign me. So I'm gonna have to edit out all the evil the evil people out of that. Just terrible. Just terrible. You simply cannot discuss this. You touch this topic and the mob comes after you. It's like you're not allowed to discuss it. If you discuss it, the mob, you cannot discuss it. It's ridiculous. Like there's no freedom of speech. And people, of course, if you're part of a gang, a rape gang, nobody's going to touch you. Nobody's going to talk about you. But if you are not part of a rape gang, then the mob is going to come after you. It's like everything is in reverse, as expected. Anyway, I have a recording, so if they want to review it, we can sit and review everything. At no point did I say anything inappropriate as far as I'm concerned. They want to ban me, whatever, what can I do? What can you do? Just have to stay away from evil people. It was at the end of the day, it was this guy. Um, okay, it was. Where is. I can't see him here. Anyway, it was a guy with a he him in his profile, which I should have known to just ban him as soon as he started, accusing me and everything, every what I said, he was accusing me, and I should have just banned him. It was a big mistake. Like people that start with the accusation, it's like they accuse me of everything. It's like the great Alex playing with fire. He started accusing me of anything and everything. Just like endless accusations. Just ban. You have to learn to ban people. Just get rid of defective people. Get rid of them. Take them out of your life. I made a big mistake. Now I'm paying for it with this headache. Terrible. Just terrible. Anyway, okay, I'm gonna go. I'll come back in like a few hours and we'll continue the saga. All right, bye bye.